Hello, hello, hello. Hello, okay. Yep, works. You can check yours.
1, 2.
All right, ready to go? All right, okay. Hi, good afternoon, everybody. Thanks for coming for this session. Our session title is Software Defined Security Reloaded. My name is Ash Palgat. I am Senior Director for Cloud Marketing at Mellanox Technologies. I have with me my colleague, Yosef Ephraim. He is the Director for Software Development at Mellanox Technologies. And then today we have Zika Wong from JD Cloud. He's a principal architect as well as product lead for their infrastructure as a service JD Cloud offering. And we're going to talk about a very interesting topic. This is the first time we're discussing this. Nobody has discussed how to improve the software-defined security performance and efficiency. So this is the first time we're going to talk about it. So without going into too much of the agenda, there's a lot of stuff here that we're going to cover. It's going to be good use of your 40 minutes, and you guys are really the hardworking people coming into almost the second last session of the day. So we're not going to disappoint you, but essentially our talk is split into two parts. One is we're going to talk about what is the OVS hardware offload technology. How many of you have heard of OVS hardware offload? Just a show of hands. Okay, I think fairly some people. So we're going to give some background about what is OVS hardware offload, and then we're also going to get into how the existing OVS hardware offload technique or technology is how it has been extended for security offloads. So that's the first part of the talk. Second part, we are going to talk about JD Cloud's deployment using the ASAP Squared, which is Mellanox's branding for OVS hardware offload technology, how they have used the ASAP Squared technology to deploy security functions such as connection tracking, and what performance and efficiency they gained in that process. So that's the second part of the talk. And then I'll summarize it finally with the key messages. But before we get into the details of what exactly is OVS hardware offload, let's talk about a survey that we conducted with a company. It's a third party called Futurium. It's a research firm. And they conducted a survey that kind of looked at the pain points of different IT infrastructure managers, directors, and CIOs. And they found out that in the virtualized infrastructure, there are a lot of things that the IT managers want to have fixed or kind of addressed. But software-defined security happens to be one of the key technologies that they want to be improved in terms of efficiency. So 78 out of the 218 people said we want to have this fixed, so about 35% in that sense. And then people were already aware of SmartNICs. As you know, SmartNICs is a big rage in the industry. It's a revolution. It's not your regular NICs or the basic NICs as we call them. The really smart NICs, there's a lot of innovative things that are happening in the smart NICs. And people who were surveyed, we actually talk about China here because we're in China. So this survey was taken across UK, USA, and China. And the Chinese audience basically told us that they think 75% of the audience told us that SmartNIC can be really helpful to isolate and stop the security threats. So that's really interesting data point. You can download this report if you like. At the bottom there's a link. It's called Untold Secrets of the Efficient Data Centers. It's a 25-page detailed report. So very helpful report. So let's talk about why do we need SmartNICs. What is the need for efficiency in the data centers? As you know, we start with, when you get a server, you get a lot of cores on it, depending on what kind of server you might have with CPU. Skylake or whatever the latest thing is, Cascade Lake, whatever it might be, you get a lot of cores, let's say 24, 28 cores, right? But then what happens is you start putting software-defined everything on it. So you put virtualization, you put security, you put software-defined storage, or anything of that kind that's software-defined. It starts eating up your cores because using a general-purpose CPU for doing all of the software-defined things, which really kills the performance. And it also underutilizes your hardware because now the cores that the application developers could use, the green cores, are now eaten up. And that's where I think the SmartNICs are really a rage, because what you can do is with a purpose-built hardware, such as SmartNICs, you can free up those cores, the red cores, that are used or consumed for the software-defined everything. And the SmartNICs are giving you back those cores so that you can either use it for your application developers to run applications, or you can give it to a tenant. In the case of JD Cloud, that they're using those cores for generating revenue. So it's very important. Let's talk about the SmartNIC acceleration strategy. What are the different flavors of SmartNIC? What do they do? So there's of course NICs out there. As you know, there's basic NICs, foundational NICs, as we call them, typically 1 gig to 10 gig speeds. These are not programmable NICs. They are simple NICs. And they have some offloads, maybe stateless offloads. That's what they give you. They're priced for the values. There's a lot of commodity NICs out there, basically. And some of our NICs also gets, the Mellanox NICs also get used into those markets. But essentially, where the whole of the value in terms of building an efficient data center, where that's shifting, is through the SmartNICs. You're putting the SmartNIC into servers to gain a lot of efficiency. For example, there is a ConnectX 6, or ConnectX 6DX. These are the SmartNICs. They are ASIC-based SmartNICs. They help you to get really best performance for your price. They help you to really improve the packet performance through hardware offloads. And they're really flexible and efficient and programmable NICs. So that's really great because they're purpose-built hardware. And they free up a lot of your CPU cores. Like I said, the red part, which is the bottleneck, is kind of going down, mostly around the data plane offloads. The next one is called the Bluefield, which is our SoC-based SmartNIC. And what happens in that case is you are really getting not only the ASICs that are already pre-built for handling the packet or network workload or storage workloads, but you also have compute next to the ASIC that are handling the data plane. And the compute can help you to also free up whatever cores have been used for compute, let's say for OVS or virtualization or even hypervisor or OpenStack platform. If you want to use any of that stuff on a compute, you can put it on a SoC NIC, SmartNIC, and that will completely free up your, your resources, right? And give everything back to the to your developers or to your tenants in terms of the compute capacity. So let's talk about what is SmartNIC data plane offload? How does it work, right? Typically in any of the networking operations, any of the networking functions, there's always two common operations, data operations. One is classification. Classification refers to matching your tuples in a packet to classify them into flows. And the second part is action, which is based on your classification. So you take the action that is associated. This is an OpenFlow model. So you classify the flow into flows, and then you decide what to do with each of the packet in that flow, based on the action that's already pre-programmed. And these are programmable NICs that we're talking about, not the commodity NICs, the smart NICs. If you look at OpenFlow, it's just basically a table-based, flexible model of a lot of different entries of match and action rules. And you have different table sizes. You have multiple tables. You can have cascading of the tables. You can have very programmable table sizes. You can scale infinitely, basically, because these tables can be cascaded. They can add it as needed basis. This can be dedicated per port, per VM, per container. All of that stuff is available. So it's really, really flexible model. OpenFlow has been out there for a long time. But the match and the action part, so on the left-hand side, this is what you can match on. So you get a packet. You can match on, for example, Ethernet layer 2 fields, so source, destination, MAC, for example, or Ether type. You can match on a layer 4 IP fields, for example, source, destination, IP addresses, or protocol type, or a layer 4 or layer 3, and layer 4 TCP UDP headers, like TCP port, source port, destination port, etc. So if you see, you can match 5 tuples, 7 tuples, and you can take a variety of actions. So there's a whole lot of actions that you can do for packet steering. And those actions could be, just switching the packet based on whatever the IP addresses are. And this is all mentioned in the OpenFlow tables, by the way, as an entry. You can do NCAP, DCAP. If you're doing VXLAN traffic, or GNU or NVGRE or MPLS or UDP or GRE, all of that can be done as a encapsulated packet or decapsulated packet in the silicon. You can also do header rewrites. You can do also hairpinning mode or counters, setting counters for your transmit, receive number of packets or bytes. All of that stuff can be done. Now, in addition to that, something that we added newly is the connection tracking, which is what we're going to focus on today, because that's about security. It helps you to track connections for stateful connection tracking offloads. So real quick recap of people who may not have known about what is OVS hardware offload. In traditional SRIOV data plane, what happens is you take the data path in SRIOV, you connect the VMs to the E-switch via a VF, virtual function, and then all the data goes directly between the VF and the NIC. There is no SDN programmability in that kind of paradigm, and that's the problem when you define software-defined infrastructure. And so in OVS hardware offload, what happens is you program your control path is through this flow offload API, and whereas your data plane is still SRIOV. So now you added a control path in addition to existing fast data path, and that's best of both worlds, and that's OVS hardware offload. Essentially, we call it in Mellanox a accelerated switching and packet processing, which is a brand name for this technology, but it's all based on open source. It helps you to get SDN controllers can program network policies into OVS that can be translated into fast data path performance and programmable control plane through the E-switch of the NIC. If I go back a little bit here to just to show the packet flow, normally the slow path is when the OVS hardware offload is not enabled, all the packets go to the kernel, right, and then they get switched in the slow path. You of course get the rules program from the vSwitchD, which is the user space component for programming the rules. But in the fast switch or the hardware's OVS hardware offload case, you will see that the fast path is programmed by managed, or data path is managed by the E-switch itself. So you're not really using the slow path in the kernel. Here's the API, that's it. Like I talked about, the control plane API for programming the rules of the E-switch is done through a Linux API, open API, called as NIC Flavors. So in addition to what the vSwitchD does normally for programming the rules into OVS data path via the standard API, right? We are also using the NIC Flavors in parallel to program those rules through the driver of the NIC into the E-switch, which is the hardware component of the NIC, which is really, really efficient. And all these entries are always in sync. So that's the mechanism that's already established in the software. What is the performance you can get? It's really amazing performance, and a lot of cloud providers, telco cloud customers, all are deploying this technology, and you get, phenomenal performance, order of a magnitude almost. So you can see with 2 cores, if you're using OVS over DPDK, DPDK is a software acceleration technology, uses libraries, versus if you use OVS hardware offload in the E-switch of the NIC, you can see that 7.6 million packets per second versus 66 million packets per second. That's almost 8 to 10x higher. And this is without consuming any CPU, because when the E-switch is offloading, it's not using any of the CPU cores. So that's really important to make sure that all the CPUs are offloaded and you're getting the best performance at the same time. So it's really, really a rage right now in the industry. And this is all open source driven. There's no vendor lock-in. Of course, the E-switch is a vendor product, right? So Mellanox has its, other vendors have it too. But it's all programmable through Linux APIs. So there's no vendor lock-in. It's all OVS integrated as well. And OpenStack integrated. So here's a quick snapshot, not having to go into every detail here, but there is kernel components that have this support for OVS hardware offload, OVS version that has OVS hardware offload, and Quince is the minimum release you need to have in order to enable this. Plus there's commercial products that are already supporting that if you're using those commercial products. So let's switch the tracks a little bit now that we have the background about how does the OVS hardware offload work. What is ConnectTrack and why is it needed? So ConnectTrack is, it takes the connections and stores the information about the state of connections. It's basically, for stateful connection tracking, you need the Linux existing mechanism called as ConnectTrack. And it uses IP tables, net filters, and has a connection database, all maintained in the Linux kernel today. There was an extension to that through OVS, when OVS got integrated into ConnectTrack. So there is a work that we did, I'll show you in a second. But essentially, each packet will be found in the database if it's existing as a established connection. If it's not, then you add that as a new established connection, assuming you want to track a connection, right? So the premise is you want to track a connection or flow to say, okay, each packet coming into this flow needs to be tracked for future, so that I can find out the state of the connection of each packet. And the states can be different. This can be new state, established state, related state. New state is when the connection is just being established. Established is when the connection is already established, and you're trying to find out if this packet belongs to a established connection. Related could be something like a TCP, FTP kind of protocol that might be using TCP underneath. So it might need a related connection information. And invalid is when the connection really doesn't, the packet doesn't fit any of the connection database information. It is also used for NATing, so without having to go into all the details. NATing is a very important use case. So how does the connection tracking work today between Linux and and OVS? There are 4 components to it. One is, OVS CT uses the same connection tracking mechanism as the IP tables and the network filter tables. Step 1 is when you receive a packet, You basically, you classify the packet and you determine what action is needed. Now the action has to be, like I said, it needs to be, one of the actions should be, hey, track a connection and see if it's a stateful connection. And so that's where when you go to step 2, you make a call to the connection tracking module in the Linux and say, hey, can you please track this connection? It'll find out if the connection exists in the CT table. And if it is, then it'll return you the CT state information. Now that's what you use to update the metadata for that particular packet about its connection state. And then you recirculate the packet so that OVS will classify the packet. Now this is all done in the software. There's no hardware offload. It's all existing using OVS CT along with the net filter or the IP tables. When you go into the hardware offload, now what happens is we are using the Linux TC at that point to kind of start using what we did before for programming the NIC in the eSwitch for ASAP squared hardware. We're also using that now to program the connection state, connection information for a specific flow. So you say now you program into the eSwitch that I need a specific flow, each packet within this particular flow has to be tracked for CT state. So that's the programming part. And that goes from the control plane. So that's where the TC will be doing. So we are extending the TC, right? So remember one thing in the hardware CT offload, we are not doing this all in the hardware. We are doing it the way it is currently designed, which is the connection establishment is done in the software through the contract module. There's no change to that. What we are doing is our hardware is enforcing the CT state. So you tell through the TC TC API that you need to track a connection state for a packet. And then once you have that, that's the control plane part. The data plane part would basically automatically do the fast switching based on the CT table information that resides in the eSwitch, right? So you don't have to go to the the kernel module to find the CT state because the first packet is a miss and the subsequent packet is a hit because the CT state is resident locally in the NIC itself as opposed to in the software. So that helps you to improve the performance a lot. So the software CT state table replicated in the hardware. It's replicated. So you can see there's a CT state that's replicated in the hardware, and that's for the 2 reasons, right? One is you want to do fast switching or forwarding match and action based on CT state, which you have to do earlier in the software. Now you're doing in the hardware. And secondly, you're saving the CPU cores because all this processing is happening again in the hardware and not going to the software. So that helps you to save a lot of CPU cores. So we're going to talk about it. We're going to see a quick demo after this, but I'm going to hand it off to Yossi to talk about software development effort and what we did as what is the demo lab tested numbers on this for this technology.
Okay, thank you, Ash. As Ash said, my name is Yossi or Yosef, depends how you wish to call me. I lead, actually last year I led the OVS offload development in Mellanox, working with Mr. Cheka here in China to integrate it to JD Cloud. Obviously, this is a generic solution. Okay, the OVS offloads is upstream. Mellanox is a big believer in upstream development for Linux community and also for the OVS and OpenStack. So at the moment that we started working on connection tracking, all the infrastructure was in place for adding the connection tracking. So actually, for the OpenStack, you just have to enable security groups, and it works. So assuming that you will have the latest Linux kernel and latest OVS, and everything is for the connection tracking specifically is being submitted these days to the Linux and the OVS and IP route. So I believe that by February 2020, it's all should be upstream, and also working with Red Hat to get it in box. So this is a generic solution. The first version we did with JD, and Cheka will elaborate later. So what we're going to show is actually, I discussed. Okay, so this is the contributions that we made. So I discussed about it. We can move on. Okay, so what I'm going to show here is a demonstration that we actually recorded from the developer desk when we tested the alpha version that we did with JD. This is the implementation of connection tracking. So the developer, you know, when we had passed the basic testing, we just started testing the offload. Okay, obviously this is the goal of the development, to offload the offload and show the performance to the managers and for the customer as well. So this is set up. We have a load generator from one side, generating UDP flows using a T-Rex traffic generator. We use ConnectX 5 hardware in both sides, both in the load generator and the device under test. The device under test runs the OVS kernel with all the necessary coding in order to allow connection tracking offloads. And we also have one VM, and we probed one VF, pass-through VF to the VM via SRIV technology. And we run a DPDK application in the VM, and we have 4 vCPUs. And it's all being done on top of VXLAN traffic network. So there is also an encap, decap that happens in the hardware, and connection tracking in the hardware. And VM is using 4 vCPUs. And as we recorded it from the developer desk, I will just explain what you're going to see, because I don't want you to get too confused. Can you slide one more? Thank you. So I want you in the demo, I'm not that tall, but I want you to concentrate on these dials, okay, on these speed dials. This one, what we call slow pass, is actually the software data pass. Fast pass is hardware data pass. And connection contract hardware is just tells you how many flows are being downloaded or programmed to the hardware, okay? And regarding, 1 minute, regarding CPU usage, you can see that, okay, at the initial state, we have, you see 400 here. 400 represents the 4 CPUs that the VM utilizes using the DPDK application. And what you see above 400 is the CPU consumption made by the hypervisor running the OVS. So let's go to the video, to the 200K flows. Yeah, no need for that. Let's go to the video. So let's start seeing moving images. So this is 200 connection, 200 connections that you're going to see that is being offloaded to the hardware. So this is just a script to configure the OpenFlow rules and running the traffic generator. So the test now begins, and as you can see, traffic start moving. So we have data running in the software, and the hardware rules is being generated and downloaded. And this is when the fast pass, the hardware is now doing forwarding. So as you can see, this is the worst case scenario for us. Okay, this is a test that trashes the cache. And what you see here is 15 million packets per second, and 0 CPU, right? You can see here that we had a spike. This was the slow pass, the software pass, and then it got offloaded, and now we have 0 CPU consumption at the host side or the hypervisor, and 15 million packets per second. This is a 10 seconds test, so it stopped. And now let's see the common case, which is not the full trash of the hardware cache. So we do it with the less flows, with 5K flows. So it's the same, just configuring the OpenFlow rules and the traffic generator, and then you will the traffic will start running. So here there are not a lot of rules, so it will be offloaded very fast. So as you can see here, we have like almost 45 million packets per second. This is the performance, and no CPU, almost no CPU usage in the host side. You know, obviously it runs Linux kernel, so it has some tasks that consumes, but the obvious doesn't consume any CPU. This is full offload, 45 million packets per second, 0 CPU utilization at the hypervisor. So with connection tracking, obviously. Okay. Any questions? No. So this just summarizes the demo. Okay, so there is best case, worst case, and the numbers that we showed.
Okay. Okay, good afternoon. It's my pleasure to be here. I'm Zhike, architect of S department from GD Cloud. I'm leading the networking related work in GD Cloud, mainly focused on the SmartNIC and the white box. Here is the agenda. I will go to the content directly. Okay, so why GD Cloud need SmartNIC? The first motivation is that we want to provide committed SLA, the service level agreement. We want to provide our customer higher throughput and PPS, lower latency and data. We also want to guarantee the bandwidth allocation to our customer. Usually it's shared by customers, but now we want to guarantee. The second motivation is to release the host CPU reserved for forwarding. The purpose is to lower the cost. So when GD Cloud designed our SmartNIC solution, we have several requirements. We also have several design considerations. The first requirement is we need to offload the data path, including the packet going through the security groups. The second one is we hope the hardware should be programmed or it should be quite flexible. And the design consideration is we need to keep the SmartNIC hardware simple and robust. We need they can provide the function like match and forward, tunnel push and pop, packet modification, and queues like policer and zipper. The second consideration is try to keep the complexity in software. Then we can introduce the new service more easier and more frequently. So when we did the research on SmartNIC, there are different flavors, like there are multiple core, NP, FPGA, ASIC, and SoC. They have different advantages and disadvantages. Like for multi-core CPU, it's easy to program, but the performance is not so good. For NP and FPGA, it can be programmable, but it's some kind of hard. For ASIC, the performance is the best, but usually the hardware can't be programmed. You can't change the logic. For SoC, usually it's a CPU plus FPGA or plus ASIC. The performance is best, it's quite flexible, but for now, it's a bit of expensive. So GD Cloud did a lot of research, did a lot of investigation, and finally, we decided to do collaboration with the Mellanox. Why? I think the first reason is their SmartNIC is quite flexible and can meet all our requirements. The second one is they have quite a strong roadmap of product. Okay, regarding the security, there is a product called security group. Usually it will define some rules to allow or deny some traffic. For example, we can allow the traffic egress from the VM and then allow the traffic, the reply traffic. But we don't allow the traffic originating outside of the VM. So usually the security group is implemented by the ConnectTrack. So how can we offload the ConnectTrack? The key point is ConnectTrack is a stateful firewall. We need to maintain the state of ConnectTrack. There are mainly two challenges when we design this SmartNIC. The first is how ConnectTrack states keep synced between software and hardware. The second one is, usually the packets go through the pipeline one by one. You need to match, one packet needs to match multiple rules one by one. So if after offloading, some rule in hardware is missing, how can the CPU continually to handle this packet? So we discussed with the Mellanox for several weeks, and finally we have a solution. This picture was taken when I was in Israel. I discussed with the architect, with the team for 2 weeks. Finally, we have a solution, and both R&D team worked together for several months. Finally, we have this great product. Okay, let's see how the SmartNIC is deployed in GD Cloud. Basically, we have two scenarios, the virtualization and the bare metal. For virtualization, our vSwitch and Hypervisor are running together with the virtual machine from our customer. And on bare metal mode, we run our vSwitch, our control process on the ARM CPU on Bluefield SmartNIC. So the x86 CPU are totally reserved for our customer. So the resource is isolated. Okay. Let's take out the performance. Previously, if we use OSDBTK with 2 cores, we use the CPU for software forwarding. With 4K to 20K connection, we can achieve about 3 Mbps. But if we use ASAP square, we can achieve about 40 Mbps. So it's about 15 times better. So it's quite amazing. The test was done with vector line tunnel with the ConnectTrack. So this result is amazing. Okay, let's see some ongoing work in GD Cloud. We are working on the user space ConnectTrack offload. The purpose is to have a better slow path performance, to have less kernel dependency, and also rapid recovery and easy maintenance. Also, we are working on the ROT-L interface support, mainly to support the loud migration scenario. We have already complete the development and is under test. We will soon have the trial phase. Okay, thank you.
I got it. Almost there. So, all right, but thank you. It's a really good presentation, Zika. Thank you so much. So you can see a customer talking about it. I really get excited because you really know that this technology works. And it's really for real. It's not just a textbook thing or something we can do as a research project. So just to summarize the talk, we talked a lot of things today. I'm sure some of it is not very clear because there's a lot to cover. But just to summarize, and you have any questions, we'll be happy to answer those after the session if we run out of time. But essentially, we talked about the software-defined security is getting reloaded. What does that mean? You have the SmartNIC X factor now added to improve the performance and efficiency of your data center infrastructure for security. That's what it means by, that's the title of this talk. SmartNICs efficiently augment the existing software mechanism for connection tracking tracking basically, right? And they augment that using the hardware offloads for faster performance and while saving you a lot of CPU cores. So as Yossi showed, you do save a lot of CPU cores. As your load increases, the CPU usage increases. All of that is being saved for you while you're getting really amazing performance, like Zika was saying, 15x, 1500%. CT offloads are transparent to OpenStack. There was a slide that we kind of skipped because of the time. But essentially, it doesn't have to do anything in OpenStack. It's all done as part of the TC offload for the control plane and the data switch, switching in the E-switch of the NIC. So there's no impact to the OVS as such, except the TC offload work. And then upper layer, like OpenStack, doesn't even know about it. So which is really great, because then it can just work transparently. And the JD Cloud achieved 15% packet rate, like we talked about, for the thousands of flows. So it's a scalable solution. Deploying the Mellanox ConnectX-5 for the ASIC version and the Bluefield for the SmartNIC SoC version NICs. And they deployed it for both the virtualized cloud, the JD Cloud, as well as the bare metal JD Cloud, which is covering both kind of scenarios in terms of either a shared hardware resource or a dedicated hardware resource for your tenant. And then ASAP squared security offloads, the CT connection tracking offloads. It's not only limited to security groups like you saw today in the use case. It can be used for anything that needs some sort of a connection tracking for stateful connection, tracking or managing. And you can use it for a variety of applications like firewalls, for NAT, CG-NAT, for example, in telco use cases, or DDoS, IPS, IDS. There's a lot of things. This is a foundational technology, it's a basic technology that really will help you to improve the performance for security for a lot of your data center applications and workloads. With that, we want to thank you. Thank you for your time. And if you have any questions, we're ready to take any questions here. Thank you.
Yeah, hello. I've got a question about the bare metal scenario that you showed us a couple slides earlier in JD Cloud. So with the bare metal, how do you make sure that the customer cannot modify the connection tracking or the security rules or the OpenFlow flows that are programmed on the Bluefield NIC?
In fact, the Bluefield have a secure mode. We can control whether to allow or not allow our customer to program the hardware. Okay. The second, from the hardware, there are different space. We can control some space with only the host can program. The customer can only program specific space in the hardware. So we are isolated.
Okay, thanks.
Yeah.
Any other questions? All right, I think we are running out of time here. Thank you so much for coming for this talk, and we'll be hanging out here if you guys will have any further questions afterwards. Thank you, bye-bye.